Okay. Hello, everybody, and welcome to the Astronomy Coffee Hangout. My name is Tony Darnell from deepastronomy.space, and I want to welcome all of our live viewers, as well as the people watching this video after the event has already happened. But regardless of how you're watching, though, we hope you'll leave lots of comments and questions for our guests that our guests can answer, because this is your chance to interact with professional astronomers and engineers live. Now, our topic today is Eta Carinae, a well-known, massive, and luminous star system located about 7,500 light years away from Earth. It is in the southern constellation of Carina and produced an outburst in the 19th century, making it the second brightest star in the sky. Now, since then, Eta Car, as it's affectionately known, has been well studied, but it still holds fascination for astronomers who are studying explosive star systems. It has two massive stars that come very close to each other every 5.5 years. And this system, the system itself, has intense outflows, which accelerate charged particles to an amazing speed. And they can produce energy bursts that can be observed in many telescopes. Now, studies with the NuSTAR space telescope, which we've talked about a lot of times in previous Hangouts as well as on SpaceFan News, they've recently helped characterize these outbursts and the type of particles that are sent our way. And our guest today will talk about their observations of Eta Car with NuSTAR, and we're going to learn a lot about this really interesting system. Before I start, though, I want to thank the American Astronomical Society and the American Astronautical Society for sponsoring and endorsing these Hangouts, where each week we try to bring you professionals in the field of astronomy and astronautics, and to discuss some of the most interesting topics in the fields today. Now, if you like these Hangouts, you can support them by becoming a Deep Astronomy Patreon patron, but you can also support them by just liking this video and sharing it around. And no comments on my technical difficulties. Yes, they are becoming a signature, unfortunately, with this. All right, so let me bring up my guests here today who are with me. First, let me start with my co-host, Dr. Carol Christian. She's in the upper left panel there. Hi, Carol. How you doing?
Hey, I'm doing well. Glad we finally hear you.
Yes. You don't even want to know, folks, what it's like to start these Hangouts these days and what I've got to do to get them going. Okay, well, good. Let me start by introducing our guests. Ordinarily, I am so busy before I get started that I hang on. Let me get this out of the way.
No, don't do anything.
Don't touch anything.
Don't touch anything.
That was my little teleprompter thingy I had to get rid of. See, I even have teleprompters now. Okay, my guest today is Kenji Hamaguchi. He works at both the Goddard Space Flight Center and the University of Maryland, Baltimore County. Hi, Kenji. How are you? Might want to wave your hand. How are you? Might wave your hand because I have all of you up at the same time. Thank you. Also joining me is Michael. Is it Corcoran or Corcoran?
Corcoran.
He's also from Goddard and from the Catholic University, the American Catholic University it's called, isn't it?
It's the Catholic University of America.
Yeah. And also Christopher Russell. And I believe you are also from Goddard. Is that correct, Christopher?
Used to be. Now I'm working down in Santiago, Chile now.
Ah, good.
Hi, everyone.
Yeah.
At another Catholic university.
Yeah.
Good. Well, welcome, everybody. I'm glad you're here. Condor Boss wants me to let Carol have the control. I don't know about that. All right.
That could happen.
Yeah, it could happen. All right, Carol, I want to, it could happen, but, it would be, I'm not, no warranty on that. Okay.
Yeah, it would be wrong.
All right.
It could happen, but it would be wrong.
All right, Carol, we're talking about Eta Car. Do you want to introduce real briefly the spirit of these Hangouts for everybody and the AAS that's helping you?
Surely. We were just chatting about this before we went on air. In astronomy departments and research, in astronomy and other sciences, we'd like to have astronomy or science coffee where we talk about recent research. And if we're fortunate enough to have like a colloquial speaker there, we invite them to coffee as well. And so our idea with this is we thought, well, we could do these online, but you know what? We could invite people online from wherever, Chile, Goddard, Florida, to discuss a particular research topic, what the motivation is for doing the research, how they did it. And luckily, the Astronomical Society has lots of astronomers who are doing research with all kinds of different facilities. And so we have the opportunity to bring that to you. And so today we're talking about some observations that, Eta Car has been observed by lots of observatories. But this new data is pretty interesting. And so we thought we'd tag up with our team here and talk to them about it. And thanks to the AAS for sponsoring us.
Definitely. Thank you, Carol. Okay. Let's start with, I mentioned briefly in the intro a little bit about Eta Car, but can one of you, and I'll let you guys decide, can one of you give us a sort of a layman's introduction to the system itself? What is it? We know it's it's about 7,500 light years away. Can somebody give us like a little basic overview of the system itself? Who wants to do that?
Kenji, you want to take that?
Oh, maybe Mike.
Come on now. Don't be
I'll
shy.
give a brief introduction. So Eta Car, Tony has just said, was one time was the second brightest star in the sky. It for most of its history before the middle of the 19th century, it was sort of a fourth magnitude star, which is not one of the brighter stars that you'd notice. You need a fairly dark sky to see it. But suddenly it became really bright. It was noted by a number of sky watchers in the southern hemisphere. And then very briefly, soon after that, it sort of disappeared. And people didn't know whether it was still there or not. We now know today, and we can probably go into this in more detail a little bit later, but we now know today it's one of the most luminous stars within our local neighborhood, and it's also one of the most massive. And I say it really is two stars, as you mentioned already, Tony. In the observations starting in the 1990s showed that the star is actually a binary system with a very weird orbit with a companion that we think is one of the brightest stars in the galaxy in its own right, but you can't see it in the enormous glare of Eta Carinae. So we've never actually seen the secondary star, but we see the effects of it.
Now, while we're talking about this, will one of these animations you sent me help sort of give the system overview while you're doing it? Like, I have this one that says Eta Car info. Can I show that?
Yeah, that would be a good one.
Please.
Oh, okay.
Sure.
I'll put that up. It's up and looping right now. I know you can't see it, but it is.
So what this is showing is a sort of a zoom in. It starts with an optical image of Eta Car. The star itself is surrounded by a nebula. It's a bipolar nebula. The video then shows a X-ray image of the system. So the system also produces strong X-ray emission. And then if I'm sort of going by memory.
Yeah, I know.
Then what it shows is it zooms in on the system. You can see the two stars, and both stars have these strong winds because they're basically blowing themselves apart. The winds collide, and that produces the X-ray emission. And I think the video ends with a sort of a swirling pattern of the stars, the companion star orbiting the larger, brighter star. And you see the effects of the interaction in the wind. It's not only happens very close to the star, but it actually extends outwards for hundreds of astronomical units, or even thousands of astronomical units, and helps shape the circumstellar material around it. So Kenji's going to talk about that strong shock and what we found, what that shock does in terms of the high energy emission.
Can I ask a question? Is it correct? Do I remember correctly that the output is periodic? Or is it continual? I mean, does it get stronger?
The orbital period is 5.5 years, and that's
okay. That's what I'm remembering. Yeah.
Yeah. So we saw a periodic change in the almost all wavelengths of light. That happened every 5.5 years.
Wow, interesting. And what's happening? Why is it doing that?
Well, so the stars, as they orbit around each other, one star passes behind the other, and the orbit is really weird because it's very elliptical.
Okay.
We know from Kepler's laws, the stars spend most of their time very far apart, and then for a very brief period they sort of fall together and whip around each other. And when they fall together, all sorts of things happen.
Okay.
X-ray emission, for example, goes away. We have a video we could show about that, and Kenji's shown that this new non-thermal component that we've seen also disappears. So that's a new result we want to talk about.
Okay. Yeah. All right.
But maybe the Chris simulation shows how that the gases flow out from the system well.
Which one?
Maybe Chris simulations. Which one is it?
It would be a hydro model.
Oh yeah.
Is what it starts with.
Oh, I see.
So
Hydro model. Got it. That's up.
So my interest is I find it really cool that we can just set up a supercomputer simulation, and then you hit enter, and then you're simulating part of the universe. So that's kind of how I got into astronomy, and Eta Car is a really cool object. So I spent a lot of time doing this. What you're going to see in the video is you have two stars. As Mike said, most of the time they spend quite a bit of distance apart from one another. So the two stars are marked by the green 5-pointed triangles. On the left panel, you're going to see density. So that just shows you where the wind material is. So you can see the material that's streaming off these two stars, but it's quite different. The one on the right, which is the secondary star, is very fast, but kind of sparse. The one on the left is quite slow, but very strong. So it's like a heavyweight fight on the left versus a featherweight fight on the right. Now the right-hand panel, unless it had changed yet, you're going to see the temperature. So that shows you where this hot gas is. So once this secondary wind hits this behemoth primary wind, the energy's got to go somewhere. And so what the energy does is it makes the gas hot. And this is what's going to emit lots of the X-rays that we end up seeing. But you should also notice that the system dramatically changes at periastron.
Yeah. Yes.
At what? What did you?
Yes, we see that.
Hang on.
Periastron.
What's that?
Yeah,
What's that?
yeah, periastron is just the jargon term for when the stars are close. And then when the video kind of resets itself, the left panel is still the same for reference, but the right-hand panel, you're seeing the X-ray emission if we had a super high resolution X-ray telescope. So this is computed from the model, but you notice the stars are going different. That's because this is from our line of sight, not just from looking on top. So from the left-hand picture, if you go to where 2 o'clock is, and then look towards the center, and then turn yourself 45 degrees out of the screen, that is the view of the X-ray emission on the right-hand side.
Now this is still in the hydro model, right?
Yep, this is still from the hydro model.
Okay.
So they're synced to be exactly linked up, but just the stars look different because you're seeing a different perspective. And you notice that when the stars get close, the X-rays just plummet. You don't see any of that red, which signifies the high intensity X-ray emission anymore.
But wait a minute, in the right panel, there's still red. That's not X-rays. That's temperature.
So at periastron, the red will drop.
I see. Yeah.
Exactly at periastron is signified by that T equals 1. So the clock there is a phase clock. So every time you get to 1, that's when the stars are closest. When you get to 0.5, that's when the stars are farthest apart. So in the right-hand panel, when you see temperature, which you're probably seeing now, you're going to see in between the two stars that little red sliver. It just disappears. And then when you see the second one in the X-ray emission, it's the same thing manifested differently, that all that hot gas will go away. So you see stuff further away, but you don't see anything in between the two stars anymore.
Okay, and Larry Keys is asking, so the apparent light change is caused by the orbit?
It's caused by the stars getting so close that, one, the absorption from the wind gets higher. So any emission that's produced is more likely to be absorbed. But more importantly, though, is the secondary wind. It can actually get up to what we call an X-ray generating speed. So each of these winds, they take some distance where they're accelerating, kind of like you're getting on a highway. You don't just start going 60 miles an hour. It takes you some time to get up there.
Okay.
So if you hit your buddy, if the primary wind gets in your way, and you don't get to go fast enough, then you are not going to generate any X-rays anymore either.
Okay.
So it's kind of like an encroachment or a suppression, but it's all driven by the fact that it has this really high eccentricity. So at periastron, the stars get quite close.
Okay. All right.
Yeah, it's probably worth pointing out that the speeds are, if you hit your buddy in front of you going in your car and generate X-rays, you have to be going at like 1 million miles an hour.
Okay.
So these winds are going extremely fast, and they're very dense by astronomical standards. So that's it generates a lot of the X-ray emission that Chris is modeling.
Yeah. So I looked this up beforehand. The secondary wind, the one on the right, that basically goes from Los Angeles to Indianapolis in 1 second. Which quite quick. That would certainly do well for Elon Musk's tube project. And then the one on the left, that's 400 so kilometers a second. So that's like going from LA to not quite San Jose.
Okay.
So it's a vast difference between the two.
All right, I want to put up this image for just a minute that you guys provided. It's called HST Chandra. It's showing right now, and I put it up because it's got a good Hubble view on the left panel of the entire dumbbell shape, because we haven't really shown that yet. And this is the entire system. It's got this 2 lobes, as I believe it was Mike that said earlier, that sort of characterize the system. And on the right panel is X-ray data. Correct?
Right. You see the 2 lobe thing as you
Correct.
On Eta Car info, that video, as you zoom in the big Carina, beautiful Carina mosaic from Hubble. As you zoom in, momentarily you can see the 2 lobe thing, but it wasn't in this color scheme, and then it faded to the X-rays.
Yeah,
so,
I just wanted
to. A famous picture. Yeah, it's good.
It really is.
Yes, it's really. Yeah.
In fact, when I was at the Institute, they had this big. Remember, Carol? They had this big lobby photo print of Eta Car.
Yeah,
it was huge. It's a very, and you can download this, by the way, as a wallpaper. But
it's a favorite.
Yeah.
People love this image, and it's been done in different colors too. Just because people like to mess with it. But anyway, Yeah.
Okay. Well, I wanted to show that, and then the Chandra image on the right hand side of this is Chandra. For those of you who don't know, is an orbiting X-ray telescope. We haven't talked about it a lot in these hangouts, so it's the only one, isn't it, guys? No. There's NuSTAR.
There are many.
And there's and it's looking at high energy particles like X-rays. It's a little bit fuzzy because while Chandra is a huge telescope and it is very high resolution, it's not super high resolution like what you said you needed in the hydro models, right, guys? So
right.
Okay.
Right.
So this can you just tell us a little bit about the X-ray emission compared to is this visible light or infrared, Carol, on the left panel? I'll get my left and right sooner or later.
It's visible.
It's visible? Okay.
It's a classic image.
Yeah. Okay, I wasn't sure. Okay, so so you want to talk a little bit about the X-ray emission coming from this?
Mike? What?
No, Kenji, I think you put this together. Right?
Oh, yeah. Well, first I have a caveat on this figure. So these 2 figures are not at the same scale. So that
was going to be another question. Okay.
Yeah. Actually, there's another figure, the NuSTAR 8. So this Hubble image is really magnified. So this bipolar lobes, this one just fit inside this red ring-like shapes in the X-ray image. So the size difference is like 10 times.
Oh, okay.
Yeah, Hubble image is
Yes. Okay, so it's down there in the center. Okay.
Yeah, that's right. Well, you may see the blue halo around the center of the point source in white. Yes. And that's the size of these bipolar lobes.
Okay.
Oh, wow.
Yeah.
Okay. All right. Okay.
So we
I'm sorry. Go ahead.
Yeah. So we actually we don't know this red ring-like shape is how this shape is produced. So we know that this bipolar lobes, that one traveled with the speed of 500 kilometer per second, and maybe this lobes is produced by the great eruptions. It's like a huge explosion event that happened in 1840s, and that ejectors just hit the surrounding mediums and they produce the hot gases around. Maybe that's the cause of this hot plasma, but we don't quite know. But anyway, so these binary systems are just at the center of the X-ray image on the right. So just in at the position of the white point source, and these ones vary every 5.5 years. So I think that the video shows how this source varies well. So can you show the Eta Carina X-ray video?
Okay, it is up now and looping. Mm-hmm. So and there's an inset panel with X-ray brightness on it.
Yeah.
Okay. Right.
So
go ahead, Kenji.
Oh yeah. Well, so this is a kind of this is not observing image. So we don't have many Chandra observations. So we measure the variation of this central source from the other satellite called XDE. That one ceased operations in 2011. 12. But so that we monitored the variation of the central source for like 15 years or something. And so that we just simulated how the central source changes in this video. But so you can see that the X-ray, well, actually the soft X-ray flux goes up when these two stars are close by, and then the flux goes down just around the periastrum when the two stars are closest, and then the brightness comes back, and then and gradually the flux goes down again. So the Eta Carina just have these X-ray variations every 5.5 years. So that's what we see from the X-ray data.
Hello?
Okay. Yes.
Yeah.
Okay. All right. So the there was a question. I'm sorry, but I got to scroll back up here on these on the comments here. But I believe it was from. Let me scroll back up just a little bit here. Okay. So Larry, no, that's. I'll ask your question in just a second, Larry. But there was one more that I wanted to. What would happen? Well, Boy, scrolling back so fast here. I'm sorry, guys. I'm getting this question. I wanted to get this one particular. Oh, here it is. Condor Boss is asking, how would a supernova of Eta Carinae or any other core collapse supernova appear to LIGO? Now, it's important that we point out this is not Eta Carinae is not a supernova, right?
That's right.
So we need to make that very clear to people.
It is important to note, Tony, though, that the energy when the star erupted was almost, not a significant fraction of a supernova's energy.
It was, oh, really? So,
yes.
So that's weird. This was an eruption that rivals a supernova, but it wasn't a supernova.
Exactly.
Well,
I mean, for a number of years, people thought the star blew itself apart. It was sort of like a mini supernova. But starting in the 1940s and then in the 60s, 70s, people realized the star's still there, and it's actually one of the brightest stars in the sky.
Yes. So yeah, but that's often, I wanted to point that out because it's often a point of confusion with this, because it does look like a supernova. Right. It does look like it would be.
Right.
All right.
How massive is that star?
It's close to 100 solar masses. The brighter component, the companion, we're not really sure. We think it's maybe around 30 times the mass of the sun.
Wow, still.
Which would still make it well. Yeah. That
Okay.
would still be one of the more massive stars in the
Wow.
galaxy.
Interesting.
Yeah, so I've got this plot up that's called Eta Car history, and this is a light curve of all of the eruptions that have happened since about 18. There was one that Kenji was talking about in 1840-ish,
Right.
and so this is a history of all of the eruptions that have happened.
Yeah, so this is the light history of the star from 1820 to roughly 2020, so almost 200 years. So you can see the blue dots there. They show the variation of the star, the brightening, and that started in 1838 and 1843. There was another one, 1890. You can see the blue dots go down. That means the star's getting fainter. And then in 1890, for some reason, there was a hiccup.
Wow.
The star got bright again.
That's what it looks like. Yes.
Yeah. And it's interesting that if you align the times of periastron passage with these eruptions in the 19th century, they almost line up very closely. So 1838, there was a periastron passage. 1843 was very close to a periastron passage. And 1890 was also close to a periastron passage. So there seems to be perhaps, or at least some circumstantial evidence that the interactions of the two stars when they get very close together does something dangerous to the system.
Now the Y scaling on this plot is enough. You need to show that 1840 eruption, but then what we're not seeing very well are the eruptions that occur every five and a half years.
Well, there are actually fadings that happen every 5.5 years. So, for example, we saw in the X-ray light curve, the X-rays sort of brighten, but then they drop very rapidly at periastron passage. You can actually see that in the visible light too. In fact, if you look at the on the right side of that plot, you see a little dip there in the red.
Yes.
That's actually a periastron passage in there.
Okay. So we're looking for dips, not brightening. Oh, okay.
Right.
But then the whole thing is brightening. Yeah.
Right.
Okay.
So we think there's like an eclipse-like event that happens when the stars. We think there's like an eclipse type event that happens when the companion star passes behind the more massive star, and that causes the emission overall to drop. But there may also be something else happening between the two stars that may drive some eruptive event. And we don't really understand exactly what the mechanism would be. So that's one of the mysteries that we're sort of trying to figure out.
Okay, let me get Condor Boss's question in because it's funny. First he wanted to know what a supernova, core collapse supernova like LIGO would look like, or would look like in LIGO. So how about one of these bursts then? What would this look like to LIGO? Would it be powerful enough to produce any gravitational waves? Forget LIGO for a minute because I think it needs to see some pretty big ones. And I don't know. Well, you tell us. Would these eruptions show up as gravitationally?
Well,
What gravitational waves?
Mike talk about it.
No, it's a good question for you, Kenji.
Oh yeah, okay. So I'm not an expert of the gravitational waves, but I heard that the supernova explosion doesn't produce the huge gravitational waves because that one explodes symmetrically. So to make the huge gravitational waves, then it has to be collapse unsymmetrically, like the collision of the binary systems. And so maybe just collapse the supernova by the Eta Carinae may not produce the huge LIGO signals. However, the Eta Carinae is really close. It's just 7,000 light year away from the Earth. So we may still see something with LIGO. I don't know.
Okay. All right. Well, there you go.
Well, I would guess if for some reason, which is not going to happen, soon, it's a thunderstorm, right? That's whatever. That if the 30 mass solar mass thing fell into the 100 solar mass thing, you might see it, but it's in orbit, so it's not going to fall in. But if it did happen, then I think you'd see it gravitational.
Right. The people have actually modeled the system to experience sort of a common envelope. So the stars basically touch each other close to periastron, or they might. We're not really exactly sure, but they might. And if that happened, and there could be all sorts of things happening.
Well, Buzz.
So, Chris, why is it getting brighter?
I think the main reason is all that dust cloud that you see for the homunculus. That is just expanding away. So the amount of material between us and the central source, it just keeps fading. The amount of material keeps decreasing, and so more of the light can leave Eta Car and then eventually reach our telescopes.
Okay, so if we did look at monitor, say we had been able to monitor in like the infrared, we might not see such a big change, right? Because the light would have gotten out through the dust cloud or something.
Yeah, or like X-rays are very penetrative. So like in the galactic plane, you can see the center of the galaxy in X-rays, but I know since I'm down here now, if you're looking with your visible eyes, you're not seeing squat. So yeah, okay. I mean, perhaps that could be
it's true, that graph is
visible. Yeah, so in other words, because it's visible and highly affected by the dust that was ejected, that's why you see this gradual but continuous brightening.
Okay, interesting.
There's actually a beautiful Hubble movie where you can see that expanding. It's about 3 frames long, but you can see from the start of the Hubble mission through recently.
That's one of the amazing things about modern astronomy now is we're able to. There was a time, maybe I guess back when maybe 50 years or so ago, everybody was thinking everything was static, not a whole lot of things changed, and now we can get time lapse movies of things like these stellar winds expanding, supernovae, but those are relatively fast events. But even galaxies rotating or nebula expanding, that's a new thing of modern astronomy that just blows me away. Adam Synergy wants me to clarify something. He's going, so the X-ray emission that you're seeing is caused by colliding stellar winds in the system?
Yes.
That's right.
Okay.
Yeah.
Yeah, thanks for that, Adam, because it's a good point that the simulations that you've seen, and also the if you look at the X-rays that we saw earlier from Chandra, then you can see that they're pretty bright, but only in certain areas. And apparently that's where the winds are meeting. Okay, let me just put up a quick picture of NuSTAR, because I want to ask a question about that. I believe it was Buzzbox Third. He's asking, is NuSTAR still going? I have a picture of it here. Is it still up and taking data, right?
Right.
Now, let's describe it a little bit. We're looking at the spacecraft. It's got this on the left side of the picture. We've got these solar panels with some kind of box down below them, and then this long boom going up to the right where there is another bunch of stuff. You want to explain to us how this is working?
Yeah. So the NuSTAR has 2 parts. One is the telescope parts, that's the right side, and one is the detector part, that's on the left side. And those solar panels are attached to the detector side because the detector needs the lots of electric energy. And so the X-rays are coming from the right side and just get reflected by the mirror on the right component. And then just the X-rays, they are focused on the way from this telescope to the detector side, and the X-rays are detected on the detector on the left side. So this is the kind of mechanism of the telescope.
So the box part that's closest to us has the primary mirror, or no? Where are the instruments, on the right or left side?
There are 2 mirrors. So X-rays are reflected twice, and that's how that X-ray can be focused. So just the mirror is on the right side, and the left side is just the detector.
Okay.
Oh, okay.
So the light comes in, hits the mirror on the right side, goes down that truss, that long truss, where it is looked at by the instrumentation there.
That's right. That's right.
Now, one thing that I think is amazing about X-ray telescopes is it's really hard to reflect them, right? Especially to focus them.
Yeah.
Chandra is so big because it uses these conical tubes, which they use what's called a glazing incidence, where the X-rays just kind of skim off the side. They're very shallow reflections. They're not like a 90-degree reflection or anything close. They're just a very gradual grazing incidence. Now, this looks like it's a pretty good reflection. What are those mirrors made of?
Well, I think that I don't quite remember. Could be the gold. Well, actually, there's the substrate and there's the coating on it, and I just forgot what the NuSTAR mirror is coated. A Chandra mirror is coated with iridium, and the other X-ray telescopes are normally coated with gold. But I just forgot what the coating of the NuSTAR.
Right. Well, that's fine. And so so this has been what compared to Chandra, is this a wider field of view or a narrower field of view? How much of the sky can you see compared to Chandra? Well,
the field of view is slightly narrower, but the key point is the NuSTAR has the wider energy band sensitivity. So the Chandra mirror can focus X-rays up to 10 kb. 10 kb is the wavelengths, but in the energy scale. But the NuSTAR mirror actually can correct the higher energy photons or the shorter wavelengths X-ray photons. So that's a big difference.
And it complements Chandra in that way, right? So Chandra can see the lower energy photons, while this one can get the higher ones.
That's right.
Okay. All right.
Well, there apparently there's. I'm looking for what is the base metal, but there's plutonium and silicon carbide and other layers that the metal is coated with, and it's multi-layer thing. But I'm continuing to look for the base metal.
So
anyway,
actually,
go ahead.
Actually, the new things of the NuSTAR mirror is that the surface multi-coated.
Yes.
So the Chandra mirror or the other X-ray observatory, the mirrors of the other X-ray observatories just have the one single coating, but the NuSTAR mirror has the multiple coatings on the surface, and so that that can reflect the very high energy X-ray photons. So that's a new technology.
Cool. Okay. Well, I want to show, because I love it, I want to show this animation that you sent about particle motions through the galaxy. Can we set the stage for this? Because it's really, I think it's really kind of cool. I know you supplied it, but I wasn't sure for what phenomena you wanted to. Do you know the one I mean? It's called particle motions.
Oh, yeah. That's not the movie, but it's just an image.
Are you sure? Oh, you're right. It is. What was I looking at? Inverse Compton. That was the one. That's the one. Yeah. Inverse Compton. Can I show that? And maybe we could talk about. Oh, this shows the two gas clouds coming together. Can we talk about that?
Oh, yeah.
All right.
Mm-hmm. Okay.
All right. I'm going to go ahead and show it, and you guys, it's going to loop while you talk.
Okay. So the Chris shows the collision of winds from two stars, right? So his simulation, well, it's just the tiny part, but actually the wind from two stars collide, and the gases are heated up, and that produces a very hot plasma. But a part of the particles are accelerated further. So this movie shows a tiny part. Tiny number of particles are just bounce between this collisional surface, and so the particles those particles are gradually accelerated to really high energy, and once it reaches to really high energies, and that one escapes from the system, and so that's how we see really high energy particles outside the system.
So hang on, we got these two particles going really fast, doing this really jiggly dance.
Yeah.
They hit each other, or they collide, and then they get accelerated out of the.
So we should ask Chris to explain.
Yes.
So what are we looking at, Chris?
Sorry, I wanted to make sure I wasn't contributing to the background noise. Yeah, so the particles themselves are not necessarily interacting. They're just bouncing back and forth across the two parts of the shock. So there's two particles shown here just for visualization purposes. But the interaction comes as now. Well, I say now, but it could be delayed. But when you see the particle come out, that red ball in the second half, it's moving quite quickly. Then it hits this photon. After it does that interaction, then you see the photon switches to X-ray, and the ball, the electron, it's going to be moving much slower.
Yeah.
So basically, some of the energy from this electron, and that originally came from bouncing back and forth in the shock before it escaped. Some of that energy then goes to the photon, to the visible light, and then it gets an energy boost and goes to X-rays. So that X-ray, that's what we can, what Kenji and Mike did, led the study on to see with NuSTAR. So that this is different type of X-rays than like from what I showed in the animations before. This is not from hot gas itself. This is the jargon term is a non-thermal population. So something besides hot gas is what's creating this, and it's this fast-moving electron hitting a visible light photon that then gives it some energy, so it becomes as X-rays, and then travels merry-go-lucky to NuSTAR where we observe it.
So non-thermal means, their particles move because they're hot, or they're accelerated from some other reason, and so that's what you're speaking about.
Yeah. So I think the going theory for again a jargon term is something called Fermi acceleration by the famous physicist who came up with it. So the particles are bouncing around due to the magnetic fields at the shock. So that's what's kind of providing why they seem to be doing a bunch of U-turns every now and again. It's due to that. So yeah, it's not just the fact that it's hot. It's another process.
Cool.
So it's just convenient for us to split it up between something that's happened because of heat, so thermal, and other stuff which is non-thermal.
So what was the NuSTAR observation?
NuSTAR was teasing out this non-thermal signature in the really high energy X-rays. So we know that the thermal only goes so far. You've seen it very well with Chandra, so we know it went up to 10 keV, but it doesn't really go much beyond that just because the gas isn't that hot. If you wanted to see 30 keV or 50 keV thermal X-rays, you'd have to have a much faster shock. So we knew that there was some limit, and then what Mike and Kenji did a great job of was getting the background of the X-ray, of the high energy X-rays low enough that you could actually see this non-thermal signature. So, and that was, I'm sure they'll be happy to jump in more about that. But yeah, that was, so we do it, you do have to deal with both. It's not like you can just tune your X-ray telescope to only look at one or the other. The X-ray telescope doesn't care how the photon was created, it just collects it.
Right.
It just says, I can see you, I'm going to record you, and then we'll let the astronomers figure it out. So yeah, if you don't have a good handle on one, then you're probably not going to have a good handle on the other.
Okay, well, I want to ask a quick question from one plot who asked this earlier, and this sort of gets to the question of what it's like inside there. He's asking, do any of these stars have any planets? That's his question. And once you answer that, just kind of give us a sense of what it's like in there. Is it very hot area? These stars must be extremely energetic. So first of all, are there any planets?
Well, very close to the stars because of the strong winds. We don't think it's a very easy place for planets to form. Eta Car, though, is weird because it does have these eruptions and it throws off material. We've identified some blobs of material called these were identified by the astronomer Gerd Weigelt in Germany. And they're called the Weigelt knots or the Weigelt blobs. And some of them are as massive as the planet Jupiter. So these things are gaseous. They're not planetary objects, but they are planetary mass objects. But no, we don't really think very close to these stars, and even other massive stars. It's a very difficult place to form planets.
Okay, let me ask Andrew Planet's question here. He's asking, could everything be getting brighter at Eta Carinae because of the same reasons the corona of our sun is hotter, but in context for binary stellar systems, but gravitational coronal attraction? I think, let me see. So our corona is hotter than the sun because of magnetic fields keeping that gas very hot, among other things. But could this be related, or could this be similar to how the solar corona is getting hotter?
It's different.
Okay.
So the
the reason I think that's important is that magnetic fields are the reason for the sun and the corona and its temperature that plasma sees. It's also very thin.
We don't. We don't think that the Eta Carinae has a strong magnetic field. So the sun has the magnetic field with the strength of like 1 kilogauss or something, but maybe the Eta Carinae doesn't have such a strong magnetic field. So the Eta Carinae is the X-ray hot plasma of the Eta Carinae is driven by the totally different mechanism, and that's the collision of the stellar winds. And those stellar winds are accelerated by the UV radiation from the both stars. So it doesn't magnetic field is not the cause of those hot gases.
Did we talk about what type of stars these are? These are presumably very hot, very short-lived stars. But what type of stars are they?
Eta Carinae is classified as the luminous blue variable. And so it's in a special stage in the stellar evolutions. But
I've not heard of that kind. So I've heard. I've heard of blue giants, but not. What did you say? Variable.
Luminous.
Luminous.
Luminous blue.
Luminous
variable. Yeah.
Wow. Well, so is this like a sub? You said it was a subclass of what? What kind of star?
Oh, massive stars.
Okay, so it's large.
Yeah, it's large, and it's not in the main sequence stage. It's close to dying, and eject lots of the gases around. So
very bright in the UV and the ultraviolet, and one of the reasons it's driving these stellar winds that we're seeing all this interaction from. So, okay, right. Yeah, good. I just wanted to make sure. Thank you, Galaxia, by the way, for pointing out the Discord server. I have it right now on my phone. I'm looking at it on my phone. So if you want to leave comments there, I'm there and looking at. There's John and Adam and a few other people. So we hear you, Tony Darnell. Thank you very much. Okay. Well, all right.
Okay,
go ahead,
so
Carol.
Now you raised the question. So that we have these LBVs, these luminous blue variables. So I assume that's the 100 solar mass star. Is it variable because it's in a binary system? I mean, are LBVs assumed to be in binary systems, or it's not known, or it's a coincidence?
Well, there were early studies. There are only a handful of these types of stars, these LBVs, known, first of all. It's thought that not all stars become LBVs. Most are not massive, and only the most massive stars go through this phase. And there was a lot of people, so because they're so rare, people don't really know exactly what they are or how they evolve. But we think that careful studies have shown not all are in binaries, where they just may be very long period binaries that we haven't never seen interact. But we think there are evolutionary models of very massive stars where the star will go through a brief period when it becomes very unstable. It becomes very bright, throws off a lot of matter because it's so bright. Basically, the star, has this radiation pressure that's pushing it outwards that's almost equal to the gravity pulling it inwards. So this is the reason the star's so unstable and goes through these eruptions, we think. And but no, we don't think all these stars are in binaries, and they do vary just because of this sort of basic instability during this stage in their lives.
So the companion is just making this whole thing more exciting.
Right. But the companion is also interesting because it gives us a way to actually examine what the how the mass is being lost from the LBV, because we have this sort of probe in place to, it's a localized probe that, is actually experiencing the wind. Yeah. So it's almost as if we, could send a satellite to Eta Carinae and ask it to probe its wind.
Yeah, so the 30 solar mass object is
right.
telling us that.
Right. So sometimes nature is nice that way.
Okay, so let me end, we're almost out of time. Let me end this with one plots question. What is going to be the end result of these binary systems? Will it survive or will they swallow one another? How's this thing going to die?
Whoa.
We need more observations. Don't say that.
And more theoretical work too.
Yeah.
More models, fun to modeling.
Yes.
Do we know? I mean, we know that this is a super luminous blue ZBZBs, but I mean, is it gonna blow up eventually? Are they just gonna swallow one another? Are they gonna, collide and then blow up? Or are they just gonna fly apart? Do we know? Have any idea?
Well, we don't. And I think it depends. It somewhat depends on where the two stars are when the one star explodes. So the more massive star will undoubtedly explode first if it hasn't exploded already. Remember, it takes like 8,000 years to almost 8,000 years to get to us from the system. So,
well, if it happened 8,000 years ago, we're good.
You're right. So the LBV will explode, become a black hole. If the two stars are far apart, they may be disrupted by the explosion, and so the companion may be flying out into space somewhere, maybe ejected from the galaxy entirely. Or if they're close together and the explosion happens and the black hole forms, maybe there'll be some sort of dynamical drag that will pull the companion in, and it will merge into the black hole. We just don't know.
Okay. Well, we are out of time, folks, so I'm going to stop it there. I want to thank my guests today. They were Kenji Hamaguchi from Goddard, NASA Goddard Space Flight Center and the University of Maryland at Baltimore County. Also joining me was Michael Corcoran from Catholic University of America. Christopher Russell, also he's down in Chile right now using the really cool telescopes that are down there. What mountain are you on, by the way, Christopher? Are you working for Parnell? Hello?
Oh, Chris, you're muted.
Muting.
Yeah, what?
Hey, that works. I'm at Pontificia Universidad Católica de Chile, so I'm not actually using any of the telescopes.
Oh, you're just down in the university down there. Are you that's because you're a modeler.
Yeah, my colleagues use it, and hopefully I can make good use of that.
Yeah, it's beautiful down there. I've only been to the Blanco telescope and down there, and the 4-meter when we were working with the Dark Energy Survey, and that's the only time I've ever been down there. But the skies there are amazing. Yeah. So,
and then the solar eclipse, July 2nd, it's coming up, so that should be fun.
July 2nd.
Yeah, 2019.
2019.
Yeah.
Okay. Good. So, all right, guys. Well, I have
fun place to be.
Good. Can we stay at your place?
Sounds like it. Yeah, we're gonna come visit.
Can we stay at your place?
Yeah.
Can I stay on your couch?
Sure. I'm going to be, my place is going to be empty because I'm going to be where the eclipse is. So
all right. Yeah, come on down.
Come on down.
In fact, you can rent it out to us. All right.
Yeah, there you go.
All right, folks. Well, that is it. Thank you guys very much. Next week, we will be doing a Future in Space Hangout where we're going to be talking about space robotics with members of the American Astronautical Society. So that's next week. And then I believe, Carol, we've got one in the week after that talking about climate change. Is it a great filter? This new paper came out. I'm going to do a Space Fan News on it before it comes out. And that'll be the last week of July. So lots of good stuff coming up. Thanks for spending your summer with us, your Thursdays, on your summer Thursdays with us. Also, thank you for dealing with all of my technical issues. I do appreciate it. So that is it for this week's everybody. Thank you all so much for watching. And as always, keep looking up.
Thanks.
Thank you.
Thank you.
That was fun. Thanks.